Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will wrap up the discussion of rectangular waveguides by looking at two topics in rather brief discussion. One is attenuation and the other one is dispersion. Now, attenuation in a waveguide as the electromagnetic wave in the form of a mode begins to propagate will be of two sources, that is it is because of two sources. One is that the material that is used to fill the waveguide, if it is a dielectric material, then you do not expect the dielectric to be perfect in the sense that there will not be any shunt current. So, this is the same thing that we have already encountered in the case of a imperfect dielectric, and we modeled this imperfect dielectric as some kind of a conductance component in a transmission line. So, in a manner that is very similar but slightly different, we will we can consider the attenuation because of the imperfect dielectric that we fill the material. However, in practice most microwave waveguides operating in the region of frequencies at 3 and beyond 3 gigahertz are usually air filled. So, there is no question of a separate dielectric material being filled. Whenever such materials are filled, then we need to consider the imperfect dielectric, but when it is air, then we can more or less neglect the attenuation caused by the imperfect air, in the sense that we can neglect the conducting current from one plate to the other plate inside a waveguide because of the imperfect air. So, attenuation because of the dielectric is present, but it can be considered to be small or negligible in compared to the attenuation introduced by the imperfect metals. Now, this is actually much more in the order of magnitude, because metals we assumed when we derived those equations were to be of perfect electric conductor, which meant the tangential electric field component there on the surfaces or on the boundaries went completely to 0 there, right. However, the conductivity of most metals is very large, but they are not as large as one would like to make an approximation towards infinity. So, most, for example, if you take a waveguide made out of copper, then the conductivity is in the range of 10 to the power Siemens per meter. You would definitely want it to be much more, so that the approximation that you made in terms of perfect electric conductor and the metal to be as better as possible. Because that is not possible, you will have to consider the effect of an imperfect metal and then see what happens to the wave as it propagates inside the waveguide, whether there would be any power lost because of the walls that are not perfect anymore. In fact, we have seen a situation that is very similar to this. We have in fact calculated all these things when we discussed the concept of a skin effect, right. So, there we had a wire which we considered, a round wire or even a planar conducting surface that we considered, and waves were all incident on that one. So, you would expect on a perfect conductor that no wave would propagate or penetrate inside, but we found that inside a waveguide there would be a small thickness of effective thickness, what is called as the skin effect or the skin depth, through which the fields actually propagate. They do attenuate inside, but to a finite extent determined by the conductivity in the form of the skin depth, the fields are not completely 0, but extend down into the imperfect metallic surface. Now, a very similar thing would happen over here. You have a waveguide made out of 4 walls. So, you have 2 side walls and then you have 2 walls, one at the top and the bottom, and these walls are all made out of imperfect metals. And in our intuitive picture of a mode, we have seen that the propagating mode can be considered as something that would be making reflections and eventually propagating along the axis of the waveguide. So, if this is a wall, then the electromagnetic wave at an angle theta would would be incident on this one, then it would be reflected, again incident, again reflected, and so and so. It would happen both in the top and the bottom wall as well as on the side wall. So, in that intuitive picture, it is clear that you are actually looking at the skin effect kind of a problem because of the light or the electromagnetic wave incident on the top wall, where the wall is now not a perfect metal. Okay. And we have seen that the average power that is dissipated when you consider the imperfect metal, and we have derived the surface impedance of an imperfect metal out there, and we call that imperfect metal as Rs, and you can show that this particular time average power that is dissipated is actually given by half Rs, where Rs is the skin resistance or the skin effect resistance that we have calculated, right. So, it was related to delta in our earlier skin effect discussion. And then you need to have the current component, right. So, we have also seen that in the case of a planar conducting surface, the current component was actually given by or is proportional to the magnetic field, the tangential magnetic field on that particular surface, right. So, in the example that we considered, you had Ex and then you had Hx or Hx, and then the current per width along this direction that we have looked at is actually related to the tangential magnetic field Hx for the case of a plane wave incidence that we have considered. So, in any wall, if you are able to find out what is the tangential magnetic field on that particular wall, then that would correspond to the current per unit width of the on that particular wall. So, IW is what we used in the previous thing. So, if I can substitute IW equal to HT, where HT is the tangential magnetic field, then the average power that is lost because of the skin effect would be proportional to. So, since the tangential magnetic field in general could be a vector, it would be HT with a vector sign. So, this is given by half RS HT square. Okay, this is the power density. You need to integrate over appropriate region in order to obtain the total average power that is lost because of the skin effect. Okay. So, we have seen this example, and for the TE10 case, if I go back and look at what are the walls of the waveguide that we have 4 walls as we said. There are 2 side walls, one at x equal to 0 and the other at x equal to a, and then you have 2 walls, one at the bottom at y equal to 0 and at y equal to b as the top wall. On this TE10 mode, what field components have do exist? The field components that exist are the z component Hz with an amplitude of H0 and a dependence in terms of x as cos pi by a times x, whereas for the corresponding Ey component, the Ey component was some constant, there were all these constants of j omega mu a whatever that is, but you are not really interested in the Ey component, you are interested in the other component which is the magnetic field Hx, and Hx is given by j beta H0 a divided by pi. This is the constant that would multiply, and in terms of the dependence on x, it would be sin pi by a into x. Of course, all these components go in terms of z as e power minus j beta times z, where beta is the propagation constant for the TE10 mode. Okay. Now, to determine attenuation, the procedure that we follow is that we recognize that the power carried by the wave or the mode as it propagates along the waveguide at any point of z is given by the power at z equal to 0, which is the incident power you are coupling into the waveguide, and if this is power is actually getting attenuated, okay, power is attenuated, let us say the attenuation coefficient for the field is e power minus alpha z, or the attenuation coefficient is e alpha, the power goes as e square. We have seen this in the case of a transmission line with losses as well, right. So, you have P0 e power minus 2 alpha z as the power that would attenuate as the electromagnetic wave propagates through the waveguide. Okay. So, if you differentiate this one, with respect to z axis, what you get on the left is dP by dz, which is the power per unit length along the propagation direction, or the rate at which the power is actually changing along the propagation direction. So, this would be equal to minus 2 alpha P0 e power minus 2 alpha z, but this is nothing but power at that particular z, right. So, power at any point z is this one times 2 alpha, and if you are only interested in the attenuation coefficient, you do not really bother about the sign, you can forget about it by taking the magnitude of all of these quantities and then obtain alpha as 1 by 2p at any particular z that you are considering, and then dP by dz. Okay. So, if you find out what is the change in the power over the along the distance or the propagation direction, which we will call as delta p. So, if you find out what is the power per unit length along that direction, then multiply this one by the power that you are using at z itself, this would give you some indication of alpha. Okay. Please note that this procedure, although seems to be intuitively correct, is not really correct, because originally we derived the fields assuming that the boundary condition would tell you that the fields must go to 0 at all of the 4 walls, right. but here we know that the fields are not going to 0. So, the fields extend slightly beyond the walls. So, strictly speaking, whatever the modes, the expressions that we have obtained is not correct, right. It is not correct because we have not applied the correct boundary condition. The correct boundary condition would have been just a continuity boundary condition, because now this is not a perfect electric conductor. However, the procedure, if you were to try and implement that one, would involve applying boundary conditions on an imperfect conductor and then recalculating all of the fields, which is very tedious. So, we adopt this procedure by finding out what is the total power per unit length and then normalizing that one with twice the power that is incident or twice the power present at that particular plane, assuming that the attenuation is there, but it is not so high that you need to re-evaluate the fields. Okay. So, that is the philosophical thing that you should keep in mind, that this method intuitively is fine, but technically may not be fine, but the results that you obtain with this method are more or less okay as long as attenuation is quite small. Okay. So, having said that, now let us try and evaluate what is this delta p by delta z. Well, on the left wall that you have, what is the tangential h component that you are going to obtain? That would be Hz component, right, on the left as well as on the right wall. But if you take this waveguide again, so you see that this is the left wall, so on which the tangential component would be along Hz, and it would be the same tangential component Hz along the right wall as well. So, if there is a power getting lost in the left wall, power must also be getting lost in the right wall, and because of symmetry, the total power lost in the left and the right side walls will be twice the power lost in the left wall, let us say, or you can look at the power lost in the right wall as well. What is Hz at the left wall? Well, Hz has to be evaluated on the left wall at x equal to 0, and we already know that Hz in terms of x will be going as cos pi by a times x. So, clearly putting x equal to 0 will cause this term equal to 1, and the value of Hz at x equal to 0 will simply be the constant H0, and then you pick off a particular unit length. Okay. So, this Hz is existing, or this Hz extends all the way from y equal to 0 to y equal to b. So, this is a side wall. On this the Hz should exist. So, this is from the bottom portion, right. So, this is the bottom wall. So, from the bottom portion at y equal to 0 all the way up to y equal to b, but luckily Hz is not a function of b. Therefore, when you pick this particular plane to evaluate the power being lost, right. So, the integration from y equal to 0 to y equal to b will simply give you a constant multiple of b. Okay. Along z, again it would, because Hz is not a function of z in this case, remember, although there is an e power minus j beta z term, because you are taking the magnitude square, that term would be equal to 1. So, if you find out what is the power that is being lost because of this side wall over here, which extends from y equal to 0 to b, and some z to z plus delta z along this particular axis along the wall, then the total power lost because of the side wall will be 2 half Rs by 2 is present, and this 2 is again telling you that the power is twice the power that is lost, and because this is constant, this would be H0 square. Integration of dy dz over the appropriate limits that we have indicated will simply provide you with b into delta z. So, the power lost because of the side wall is Rs H0 square b into delta z. Okay. For the bottom wall, what would be the situation? Let us go back and look at what is the situation for the bottom wall, right, or the top wall, does not matter, whichever that is. Again, by symmetry you can see that they will be equal. So, you can just evaluate the bottom plate as such. So, this axis is along z, this is along the x axis. So, what tangential component you have here on the bottom wall? You have a hx component, right, which is tangential. You have a Hz component which is also tangential, because the bottom wall is actually at y equal to 0, and both quantities are not functions of y, right. Hx as a function of x will be in the form of sin pi by ax, whereas Hz as a function of x is actually in the form of cos pi by a into x, and neither of these quantities reduce to some kind of a constant. Therefore, you need to carry out the full integration if you were to consider the power being lost in this hatched area, okay, which would extend from y equal to 0 all the way to, it will be from x equal to 0 to a and z equal to 0 to some delta z or z to z plus delta z. Okay. So, x equal to 0 to x equal to a. So, if you find out the power lost because of the top and bottom walls, so let us call this as the top and bottom walls, that would be twice, right. This is the total power that is being lost. So, 2 Rs by 2 anyway exists, the constant H0 square would come out, right, and then integration over z will simply pull out delta z, but whatever the integration that you have, in terms of this one, that would still be present. So, you have 0 to a cos square pi by a x dx, and this entire thing integral 0 to a sin square pi by a x dx. So, the constant as I wrote was something like j beta h0 a by pi. So, actually you should put this one into hx. So, this one goes to here, the magnitude square of this, of course. So, this goes into this one, and then for this h0 it would still be h0 as such, right. So, if you do this and then find out what would happen to this overall integral, well, you can show that after you found this and then divided by the power carried by the TE10 wave, which we actually solved it in the previous module. So, the attenuation coefficient alpha is given by 2 pi square Rs divided by omega mu beta a cube b times b plus omega square a cube divided by 2 pi square into c square. So, this is a expression for the attenuation. In fact, this expression that we have obtained is only for the TE10 mode. You can find out the expression for any other mode, because you know what is the corresponding TE mode solutions or the expressions for the electric and magnetic fields, and then you actually have to find out only the tangential magnetic field on the walls and then substitute them, integrate it. Okay. I leave this as an exercise for you to find out what happens to the attenuation coefficient of TE-Mn modes. Okay, I will leave this as an exercise. It is not difficult, it is simply tedious because the walls will not have nice behavior in terms of the magnetic fields being function of only one variable or being a constant, as we have found in this particular case. So, this is the situation for attenuation, but we are also interested in asking what happens if I take a pulse, okay, or a pulse like waveform, and then modulate this pulse like waveform onto a mode that is being carried by the waveguide, and then receive this mode at the output end of the waveguide, right. So, and if I receive that mode, the main question that I am looking at is whether the mode has attenuated. Well, if the mode has attenuated, I might compensate it by either putting it through a gain element, an RF gain element, or by increasing the power at the input side itself. But I am actually getting, I will be very worried if the pulse that I obtain at the output is not the same shape as the pulse that I send at the input, right. So, the waveguide might not be very long, but even if this waveguide is about 10 centimeters or about 9 centimeters long, and if the pulse input is not maintained in shape, right, in terms of the duration, in terms of the amplitude variation that you would see with respect to time, if it is not maintained at the output end, then this waveguide is pretty much useless because it is distorting the pulse, right. Any distortion would not be present for the TEM kind of a mode, okay. That is something that you can show. I will leave it as an exercise for you, because for the TEM mode, the only effect, because the phase velocity will be completely independent of the frequency, right, because phase velocity for a TEM like mode inside a medium plane wave, for example, will be just 1 by square root of mu epsilon, right, where mu and epsilon are the constituent parameters. So, for a TEM situation or for a TEM mode, if you consider a pulse and the pulse has all like an infinite number of frequencies, because Fourier transform tells us so, each frequency component will travel through the mode, through the waveguide at the same phase velocity, and when you reconstruct them back, then there will not be any change in the pulse shape. So, TEM modes do not distort pulses, okay. There is another way of looking at it. While phase velocity is the ratio of omega to beta, beta is directly proportional to omega. Beta is equal to omega times square root of mu epsilon, and that is the reason why omega in the numerator and omega in the denominator cancel with each other, making the phase velocity independent of frequency, okay. So, this linear dependence of beta with respect to omega, that is if I double omega, beta will also double, right. So, in order to maintain the same ratio given mu and epsilon values. So, this linear relationship can be shown to be equivalent of a pure phase delay. So, every component gets delayed and every component gets delayed by the identical amount. Therefore, there is no problem when you put the pulse components back together in order to have the original pulse shape. So, there is no distortion because of this. In a waveguide though, this situation is not correct, because beta is proportional to, or beta is a nonlinear function of the frequency f. Why? Because beta is equal to, or beta at least has a factor which is square root of 1 minus f by fc whole square, or fc by f whole square, right. So, because of this factor square root of 1 minus fc by f whole square, the value of beta with respect to frequency f is not linearly related, it is non-linearly related. And what it means is that different components actually travel at different velocities, leading to interference among the components at the output and distortion in the pulse. Okay. Let me look at that scenario in a very kind of a brief manner. I will leave most of these statements to you. The big picture is what I am planning to talk to you about. Okay. Suppose I have at z equal to 0, okay, that would correspond to the input of a waveguide. If I have the electric field of a particular mode, let us say it is just a TE10 mode that I am considering, if that electric field would be some pulse like with respect to time and has been modulated in the time domain as well. Why should I modulate? Because the modes have a cutoff frequency. So, you have to actually operate at the non-zero carrier frequency in order for this pulse to propagate. I am assuming that the pulse has its frequency response centered at omega equal to 0, making this pulse to be a baseband pulse. Okay. So, if this with some constant E0 in case you want, if this is the electric field of the mode at z equal to 0, I am concerned to find what is the expression for the electric field, or what will happen to this electric field at some z where z is greater than 0. Okay. I can do so by first looking at E of 0 into t as a inverse Fourier transform, right. So, I can actually think of this fellow as the inverse Fourier transform, which would be some p of omega, or you can think of this as p of omega minus omega 0 e omega t d omega, right. So, I can think of this fellow as having, so if this is p of omega at omega equal to 0, this is the pulse spectrum. So, this p of omega minus omega 0 will be situated at the carrier frequency omega 0 with the same shape, it just has been shifted in frequency from one frequency to the carrier frequency, right. And intuitively Fourier transform can be thought of as many spectral lines, that is each of these spectral lines have a different amplitude as determined by this particular graph, and then multiplying that one with the carrier e power j omega 0 t, you are simply putting them back together. So, intuitively this is many frequencies each having an amplitude. So, this instead of considering this as a function, now consider this p of omega k minus omega 0 as amplitude of the kth frequency, right, d omega. So, if you just think of this way, what you are doing is putting many sinusoids of different amplitudes together. Now, that is essentially what Fourier analysis is telling you. Okay. So, once you put this one back, you can think of this as simple sinusoidal plane waves which would begin to propagate, right. So, if I want to find out what is the electric field at some distance delta z from z equal to 0, I am propagating to z equal to delta z, this will be given by 1 by 2 pi. Each of these terms here will undergo a phase shift, right, and the phase shift will be proportional to, or it will be equal to beta of omega k into delta z, right. Previously this beta of omega k was omega k into square root mu epsilon for the TEM case, but for this case it is not, it depends on omega k. So, putting back together is very simple for me. So, I can rewrite this one as p of omega minus omega 0 e power j omega t minus beta of omega into delta z. So, this is how the field would look like after you have propagated over a distance of delta z. If you want to proceed any further, you need to know what is beta of omega. Okay. Turns out that if beta of omega is this way, so let us say this is at omega and this is with respect to beta, if this is the way in which beta and omega look like, okay, or maybe I can shift omega and beta over here. Do not worry about what I am actually looking at. So, I am just interested in trying to show you what we normally do. Okay. So, normally what we do is when we are given beta and omega in this particular manner, so you look for the carrier frequency omega naught, and then you have a carrier, you have a pulse around that particular carrier frequency, which means that the total frequency range would be this one. So, the curve that you are looking at is actually this nonlinear curve given in blue line, which represents the interesting range for omega and beta relationship. Okay. In that range, with omega 0 as the center frequency, I can expand this beta of omega in Taylor series as beta of omega 0 plus omega minus omega 0, that is at any frequency omega around omega 0 I can expand using Taylor series times beta prime evaluated at omega 0 of course, plus omega minus omega 0 whole square by 2 beta double prime. These terms would continue to exist, but we will terminate the expansion over here. Okay. If I terminate the expansion over here and then denote this beta prime as beta 1, beta double prime as beta 2 and beta at omega 0 as beta naught, I can put this back into the expression for the electric field at delta z. So, I obtain the pulse spectrum P of omega minus omega 0 e power j omega t minus beta z e power minus j omega minus omega 0 into beta 1 z e power minus j omega minus omega 0 whole square by 2 into beta 2 into z, right. This entire thing integrated over d omega. Now, you have e power j omega t minus beta naught z. If you multiply and divide this one by e power j omega naught t, that is you multiply by this identity right inside the integral, and you can do that because omega 0 is a constant in this integral. So, you can pair off this e power j omega t with e power j omega naught t, or you can pair it off with e power minus j omega naught t, and then you have e power j omega naught t and beta naught z, which you can pull it out. Okay. Long story short, you have E at z of t as the carrier e power j omega 0 t minus beta naught z, and inverse Fourier transform of e power minus j omega minus omega 0 square by 2 beta 2 delta z with the original pulse that we have looked at, which is omega minus omega 0. Okay. This entire thing evaluated at t minus beta 1 delta z. I leave this as an exercise for you to show, is just combining the terms that we have talked about. Okay. Let me make a few remarks over here. The carrier that we had e power j omega naught t would propagate and then give rise to a pure phase delay, right. So, that delay was given by beta 0 into z. Since it is a single frequency e power j omega naught t, this is what you expect. A single frequency would undergo a simple pure phase delay. Okay. But when your pulse you have multiple different frequencies, then the correct expression that you are going to obtain at the output or the after the propagation will involve two things. One is time has been replaced by t minus beta 1 into delta z. Okay. This beta 1 is the ratio of d beta by d omega, or rather it is a differentiation of beta with respect to omega. Since omega by beta is the velocity, d omega by d beta is what we call as the group velocity. So, beta 1 into delta z, or beta 1 into z in this particular case, beta 1 into z will be z by Vg, okay, where Vg is the group velocity. So, you have beta 1 as 1 by Vg, and then you have beta 1 into z as z by Vg, which is actually denoted by tau g, and we call this as a group delay. Okay. So, you have a pulse which undergoes a group delay, which means the peak of the pulse travels more slowly than the carrier, and this would be all right if beta 2 were to be 0, that is all that you would have obtained. So, the pulse is propagating with a group velocity, experiences a group delay, but because of this e power minus j omega minus omega 0 square by 2 into beta 2 z, the actual pulse that you are going to obtain will be the inverse Fourier transform of this nonlinear phase factor times the original pulse, and depending on what pulse you have given as an input, you will see that when beta 2 is not, beta 2 is present, there will always be some kind of a distortion. For a simple Gaussian pulse, as you start at z equal to 0, and as you begin propagation, the corresponding pulse drops both in amplitude as well as expands out. This is called as a dispersion induced pulse broadening. Okay. So, this is the effect of dispersion, and dispersion by itself means the nonlinear dependence of beta with respect to omega. So, these results are easy to evaluate. I will give this as an exercise to you. You can look at that one. Thank you very much.